Linear regression asks the question, what linear function fits the data best? Well, let's get some data. We'll use the same data set that we used last time, Anscombe's data set number 1. Now, when we talk about a linear regression, right, it's a linear function. So it's our y equals mx plus b. Well, we could do a plus bx, right, is the more statistical way of writing it. Another way, a more algebraic way of writing it would be, of course, ax plus b. But this isn't algebra, it's statistics, so we use a plus bx. And there's this y hat. This distinguishes data from prediction. Y hat is an estimate or a prediction of what the y value should be. It's not actual data measurements. So if we want to calculate by hand our a and b values, we can do so using our sample standard deviations. R is our correlation coefficient. Y bar and x bar, of course, are the means of the x and the y's. All of that we can get using our 2var stats, which is over here, x bar, y bar, sample standard deviations, and of course the R we got in the last video. So now it's just a matter of plugging them in. Here we can get our b. You would always get the b first. Here's our R value from the last video. And then you plug the b value in, and you can get your a with, of course, your y bar and your x bar. And you have your linear model, right? Your linear regression. Right? We can graph it. Seems to fit pretty nicely. We have our correlation coefficient and our linear regression. Now, of course, we can do this on the TI-84. I did show it in the last video, but I can show it to you again really quickly. Here we still have our data in L1 and L2. We go to Stat, Calc. Right here are all the regressions. You can do quadratic regression, cubic, quartic, right? Linear in algebraic form. Number 8 is our linear in a plus bx form. Now what I can show you, which is pretty cool, is here store regression equation. Right? What we can do is store the results automatically into y1. So we can do vars, and then over here we have y vars, and function variables, so that's already number 1. And here's, we could store it in any of them. I'll pick y1. And now when we calculate it, here it gives us our a and our b. It also gives us our coefficient of determination and correlation. And if I go over to y equals, it's already stored it into y1, which can be very, very convenient. So now, let's continue talking about something a little else. Curve data. Now, you do a linear regression with clearly curved data, you're still going to get a straight line. You go through that process, either the calculator or by hand, and we get a nice straight line that goes through this curved data. Is that really the best model? Probably not. But if we don't actually look at the graph of the data, we'll never know. And if we look at our correlation coefficient, right, we still get a correlation coefficient, even though the form is curved, right, when we're still doing a linear regression. And if we compare that with what we did before, with Anscombe's data set number 1, look, the correlation coefficients are identical, and in fact, the linear regressions are identical. That's the cool thing about Anscombe's data. There's actually 4 data sets, and they all come out with the identical R and the linear regression, which is pretty cool. Clearly, though, the data sets are different. And so this is really illuminating the point that just getting the correlation coefficient or just getting a linear regression is not enough in and of itself to fully describe a data set. Because here they're identical, but the data is clearly not identical. That's why we talk about form. That's why we need to calculate coefficient of determination. We need to talk about residual plots. There's going to be a whole set of things that we all need to do so that we can describe the data sets very clearly without any ambiguity.